Hello, physics. Today we are looking at Newton's laws. We're starting a new mod, so this is mod 5, and you'll be starting a new section in your notebook, and you'll be writing this on day 1 notes. So let's begin. We're going to discuss Newton's laws, and starting with Sir Isaac Newton. He was known as a great physicist in that he totally revolutionized the thinking of his day. And Newton was doing his thing between 1642 and 1724, and he was a pronounced Christian. He studied the Bible, and he felt his main focus, he did a great work on the study of the book of Daniel. He felt like that was really important. We're going to look at what he did to revolutionize the physics world, because the time when he came on the scene, people thought that all objects wanted to stay at rest. So make notes as I write things on the board or speak things that are important. Mr. DeBloom will check your notes for completeness. He'll go by and give you a note score. So it's very important that you take notes. So the thinking of his day was that all objects want to stay at rest. So an object on a table that is at rest will want to remain at rest, and an object that is moving has had a force applied to it and is moving down the table, it will want to come to rest, and you'll see it go slower and slower until it does. So it made sense to those observations, but Sir Isaac Newton could see a little beyond that, and he came up with the first law, and his first law, and let's call it that, Newton's first law. Today we'll do 2 laws, and we'll stay on law 2 for a while and unpack that, and then at the end of the mod we'll do his third law. Alright, his first law is an object at rest will stay at rest. So that was not anything revolutionary, because it agreed with what the observation of its day was. But then an object in motion will stay in motion unless acted upon by outside unbalanced force. So you can, at any time, you can pause this video if you need time to write things out. So the thinking of the day was found to be false in that it didn't tell the whole story, because it thought that every object in motion also wanted to be at rest, and he said the exact opposite about objects in motion. They want to stay in motion unless acted upon by an unbalanced force. So why does an object that is scooting down the table come to a rest? And the answer to that, as we know, is because there is another force at work, and that unbalanced force is the force of friction, which we'll deal with a lot in this mod. Alright, so let's talk about how we observe this law in a practical way. If you're riding down the road in a car, and the driver brakes suddenly, and you're the passenger, your body will continue with the velocity of the car, because according to Newton's law, your body was in motion, it had the velocity of the car. When the car stopped, friction was applied to the wheels of the car, so an unbalanced force applied to the wheels, the brake pads, caused the car to stop, but no such frictional force was placed on you, so your body will continue to move forward. And you will feel there is some friction between the back of your legs, your butt, and the car seat, so that will help you stay in place. The car belt, the seat belt, will help you stay in place, or the windshield or the dashboard that you hit will help you stay in place. So there will be an unbalanced outside force that will be the only thing that would cause you to also come to a stop. Alright, what about, I know when my third child, when she was a young girl, we would go pick up pizza, and her job was to hold the pizza on her lap in the front seat. That was it. So we got home, and there's this little spot this big, and it's between the seat of the car and the door on her side, the passenger side. When I had to turn to the left, the pizza wanted to go straight, but as the car turned, that little spot became the spot where the pizza box went. And she did that maybe 10 times in her young life. So that is the curse of Newton's first law. All right, so let's talk about a situation where, another situation where you can feel Newton's first law. Could be any time that you're in motion. Say you were in a bike and you hit the brakes, or if you were on a bike and you accelerate. Let's do the acceleration part. So you're going and then suddenly you go quicker, your body will feel, because your body is going the velocity of the bike speeds up, your body will feel, you will feel a thrust backwards. So in its attempt to stay at the same velocity it was going originally. And of course, if you brake, you can feel the thrust of your body forward because your body is in motion. It wants to stay in motion. The bike under you has braked. You will continue, and of course, you'll feel the pressure in your arms to hold yourself in the seat. So, Newton's first law. Newton's second law is going to come in a mathematical way. Let's see if that shows up. This looks good. And that is the sum. There's a symbol, the sigma symbol. It means the sum of. We'll be using that in math class this year as well. The sum of the forces equals ma. So we have an object, there's lots of forces on that object. The sum of those forces equals ma, where m is mass and a is acceleration. All right, so we can stay here with this equation for, I think, several days. So this has a lot to unpack. But the gist of it, the basic gist is, when you push or move, push or pull on an object and you apply a force, that force will equal the mass of that object times the acceleration of that object. So let's talk about whether it is a vector or a scalar quantity. It turns out that mass is that a vector or a scalar quantity. Write down above it whether it's vector or scalar. Then do the same for acceleration. Is it a vector or a scalar quantity? You'll recall vectors have a size, a magnitude, and a direction. Does mass have both a size and a direction? Well, mass is measured, say, in kilograms. So we say that object is 4 kilograms. We don't say -4 kilograms or 4 kilograms to the west. So direction, when it comes to mass, has no meaning. So it only has size or magnitude. So mass is scalar, and acceleration we've already met. We know it to be a vector quantity. So do you suppose that force is a vector or a scalar? Well, since we're multiplying scalar times a vector, what do you think we will get? Perhaps intuition or a bit of good luck will tell you that it is also a vector quantity. So it does have a size and a direction. So that's force. Another thing we need to understand about force is what it is. Force is a push or a pull. All right, so we intuitively, if that didn't show up, please write it out anyway. Force is a push or a pull. On an object, I know this doesn't show up. I'll adjust the screen. To change its acceleration, So force is a push or a pull on an object to change the acceleration. All right, anything that goes on the board goes in your notes. Let's talk about the units for force. Since we know the units for mass and the units for acceleration, can we not multiply them together and get the unit for force? Let's say force equals, force can be measured in the unknown unit. Mass is, a typical mass is kilograms, and the typical acceleration is meters per second squared. So if I multiply these two together, I get kilogram meters per second squared. This times this. Kilograms and meters are in the numerator, and second squared is in the denominator. All right. So we do have, this is our unit for force, kilogram meters per second squared. However, we did not like that balky of a unit, so we renamed it in honor of Sir Isaac. It is the Newton. So, you must know the unit for force is a kilogram meter per second squared. I have a little activity to help you remember that, and I will perform this when I come back. I will bring in various kinds of fig newtons, and if you forget what the unit for force is, I will force a fig newton in your mouth. So you will remember that force is measured in newtons. That will be a memory aid. Another way we can do that, kilogram meters per second squared is totally metric. Let's cross the boundaries of the ocean and go to the United States, where we do everything a little bit differently. And what units do we use for, non-metric units do we use for force? And it turns out mass is measured in slugs, and acceleration is in feet per second squared. So another unit for force, this one is the metric, and this one is the English, which they call English, but it's in the United States. Force is measured in slug feet per second squared, and we rename that the pound. So, alright, so if you weigh 120 pounds, it's really 120 slug feet per second squared. Alright, the bell rang, there's going to be a class coming in, so I'll return and finish this talk on another part. So, see you then.